tax, ang makaka-avail lang ito ay internet lang. Ang nag-cost na nag-avail is 8%. Okay? And another, kailangan
Okay, good afternoon, everyone. Welcome to the International Perspective Series webinar series entitled IoT Use in Coffee Production, a Case of SME in North Sumatra. So, before we officially start our event today, I would like to introduce myself. My name is Johanna, and I will be acting as the MC for today's event. And I would like to remind the participants to open your camera and use the virtual background that have been sent by my colleagues in the chat box. Okay, moving on, I would like to give a brief introduction about our project here. So, the International Perspective Series webinar is a series of international online knowledge lectures jointly led by the Semiotet China Asian Technical Education Cooperation and co-hosted by the Southeast Asia Youth Sustainable Development Foundation and GoStudy. The program is expected to invite 1 until 2 school faculty members to give webinars each month, aiming to enhance and enrich the growth of knowledge and broaden the horizons of learners in the Southeast Asian region by inviting experts from different countries and fields to provide high quality and universalizable online lectures that will help learners to acquire specialized knowledge through knowledge sharing and cross-cultural understanding. Okay, now that we have already known what the project is all about, we're moving on to introducing our speakers for today. So there will be one speaker today, and his name is Dr. Lukman Adlin Harahap. He is a researcher and assistant professor of Universitas Sumatera Utara in Indonesia. He has completed a lot of research, such as pengenalan jenis roasting biji kopi menggunakan algoritma K-nearest neighbors (KNN), and aplikasi sistem informasi geografis dalam manajemen kesehatan subkarai daerah aliran Sungai Ular, and also publish a lot of journal articles such as soil moisture monitoring system using wireless sensor network, energy and economic analysis of ice cream stick production with Brent tank machine, and design of web-based pre-production managerial information system for horticultural product farmers. His professional fields are, of course, agricultural engineering and computer science. Now, everyone, that we have already known who our speaker is, I will be giving the time and also the screen to our speaker here, Dr. Lukman, to share his presentation and also his materials. Dr. Lukman, the time and screen are yours.
Thank you very much, Johanna. Good afternoon, everyone. As I've been introduced, my name is Lukman. I'm from Universitas Sumatera Utara. Currently, I'm teaching in Department of Agriculture Engineering and Biosystems of Faculty of Agriculture, the Universitas Sumatera Utara. So today we are going to talk about the use of IoT in coffee production in the case of SME, since oh wait, I haven't started the presentation yet. So why SME? Because this for the small scale production only. Okay, we're gonna start with the overview. So Indonesia is number 3 producer of coffee. Well, most of the coffee in Indonesia is Arabica. As you mostly have known, um, Robusta, which is about 80 to 90% of national production, and Arabica. But the Arabica in Indonesia is very famous uh, for some uh, cultivars. So it is expected to be produced by 25.45 million bags in 25 to 26. And this is the growth is steady in Indonesia. But we have also small daunting problem, if I may say. Most of the coffee production is held by a smallholder, which is by definition they have like less than one hectare land. So basically, they are small time for farmers, which is relying on uh, small production and also small land. And they are facing the problem of the renovation of the area because small farming means small um, resource to begin with. So it means that there is not much available to replanting of the coffee tree trees. Uh, and also the problem of Indonesia coffee production is it is a lot lower than the coffee production uh, when compared to the competing countries like Vietnam, for example. Vietnam, which is just one rank above Indonesia, they have like 4 times higher productivity compared to Indonesia. So, but still, Indonesia is number 4 in the world. So we go on to the case of North Sumatra. Why not Sumatra? North Sumatra is deemed as a hub and primary source of high quality specialty coffees. Well, not only North Sumatra, but I think the whole Sumatra. Uh, North Sumatra itself has ranked fourth of in Indonesia production, and this is the number of 2023. The size of the plantation is approximately 98,600 hectares, which is sizable, and they produce roughly around 87,900 tons of coffee beans. And along with North Sumatra, there are provinces as well, like Aceh as well, and Lampung, which is famous for kopi luwak, if you ever heard of. Okay. So in North Sumatra itself, aside of kopi luwak, we have the Mandaling coffee, which is known for sweet caramel spices profile of taste, and Lintong as well, which is tastes like a dark chocolate. It have caramel and nutty taste with a hint of orange. I mean, it's smells tastes like a bit of orange, and also in Sidikala, and this is the one of the most famous in North Sumatra. So this is the high quality Robusta uh, and very tasty indeed. So if you ever come to Indonesia, you should buy this one. And it's been sold in boxes as well. So it's been commercially produced and processed. Um, what are the challenges? So, well, since the production is held by small farmers. We have a stagnant production and declining consumption, which is not very much actually, but we have the decrease, which is like 1.90% per year. And the productivity gap, as I said before, it's 4 to 5 times lower. And these are the challenges. I think most of them I already mentioned before. But with the challenges, we have also the opportunities. We have consistently growing exports of coffee throughout the world. So I've been reading about how Starbucks also use some coffee beans from Aceh as well. So it is a very highly chance of Indonesian coffee will go travel the world. And also one of the closest friend of mine also have export companies that actually export coffee to many places like to I think this year they export to Germany, and last year they said they export to South Korea. So basically it's really growing. And also Indonesia is known for the specialty coffee like Aceh Gayo, Mandailing, and Luwak. And this Luwak mentioned very much in the international stages, like in one of the movies. I forgot what was the title of the movie, but the main character specifically mentioned Luwak. And also in the terms of scientific advancement, Indonesia also have joined the Innovia Global Breeding Networks. So basically, Indonesia have a chance to develop another climate resilient and high performing varieties that can be used by local farmers to boost their production. And also, even though the productivity is stagnant, we have the expansion of cultivation areas, which means more and more people is planting coffee. And also the ecosystem of modernization. So nowadays, there are more and more facilities producing coffee beans to be consumed and to be exported readily in Indonesia. Okay, so we get after we talk about the background of the coffee production in Indonesia, we will talk about the why roasting matters. Why do we have to roast the coffee beans? So for you that is not familiar with the coffee, so coffee beans are not black. So when they are freshly cultivated, freshly harvested, they are not black. So the coffee beans are mostly red or green, have a green exocarp. So to be processed, the exocarp first removed, and they will have the beans inside. So the beans, which mostly are colored green, and it will be dried first before consumed. There is much more process to be done before that. So basically, coffee beans, there is coffee beans readily be roasted for the process is not black. So they are mostly green to white color. So why roasting? So roasting serves as the process of changing the physical and chemical properties of a coffee bean. So it is mentioned here that it will involve heat transfer, thermodynamics, and chemical transformations. So roasting will have the role to extract the flavor of a coffee bean. So without roasting, we couldn't really taste the coffee as we know. So what happened when the roasting is done? So first is weight loss and density. So basically, coffee bean will have weight reduction up to 28% due to the evaporation, and also organic compounds inside the beans to be released, and also density decrease significantly to volume increase. And the porosity density decrease means it is a lot less dense than it's started. So it's most like, so if you can imagine a popcorn, a change of corn to a popcorn, it is much more like that. And also the porosity, since the volume is expanding, there are a lot of pores in the beans. So the beans become much more porous, which means a lot of pores inside, and there's a lot of spaces inside the bean. So this is allowing the extraction of flavor compounds in the brewing process later. So this is the basis of the coffee roasting. So in the charge space, this is the very first process. This is where the coffee beans get inside into the drums. There is a specific temperature to be attained before the charge process is done. So it is around 180 to 200 degrees Celsius. So after the beans are poured into the canister, so it is charge phase, the temperature will drop. So that is the first one. So the temperature will drop, and it will drop to around 90 to 105 degrees Celsius. And after that, the temperature will back rising again. So that is why it's called turning point. And after that, the temperature will continue to rise up to 160 degrees. This is the drying phase. At this temperature, at this phase, the coffee bean is experiencing a lot more evaporation. So this is where the drying phase done. So after that, in the temperature of 160 to 190 degrees, the Maillard reaction is happen, which is often called the flavor building zone. So at this phase, melanoidins and also another compound is being extracted. So this is also where the aroma is being built. And the temperature will continue to rise to around 195 to 203 degrees Celsius to experience the first crack. So the first crack means, so it really is a crack. I mean, if you are familiar with the roasting process, you will hear the crack at this degree. So most of the experienced roasters will know when the first crack happened. There's actually an audible crack to it. When the first crack happened, this is where the internal pressure causing the beans to expand. This is the marking the beginning of development phase. So in the development phase, after that, this is where the caramelization process is happening. So this is where the flavor, the caramel, the sweet taste, the sweety taste of a coffee bean is being developed. Up until 215 and to 225 degrees Celsius, there will be a second crack, which is a crack that is a lot less audible than the first one, but this marks almost the end of the process. So in the second crack phase, this is where it enters the dark or French roast territory. I mean, this is the very, very end of the roasting process. This is where the taste of bitter and smoky taste is formed. And the last phase should be the drop and cooling. At this phase, all of the process should be stopped. And the bean should be cooled immediately to halt internal chemical reactions and to preserve delicate flavors. I mean, if this process is led to be naturally stopped, so without help, the beans will experience over roasting, and it will lose the taste and the aroma that has been developed during this step 4 to 7. That is the roasting phase. And in this case, there are two kinds of roasting. There are fast roast and there are slow roast. Fast roast means that you are roasting for a shorter duration, but you are using much higher temperature. In the slow roast, you are using a lower temperature, but you will take a lot longer time to roast. So both of the process, it's valid. I mean, but it's not for every beans out there. So we can see here that fast roast is very good for the high density or high altitude beans, and the slow roast is very suitable for the low density or low altitude beans. So both of the roasting mode is used, but it's for different beans. Okay, after we are talking about the roasting, so we are going to talk about why cooling. So since we know that the roasting would make the coffee beans ready to be extracted for flavor and also aroma, and cooling actually has to be done for several reasons. The first reason is the termination of residual chemical reactions. So basically, why do you have to cooling? Why do you have to cool down, to do cooling on roasted beans? So as I said before, when a coffee beans are roasted, there are chemical process that has happened, right? So if the beans are not cooled, this reaction will go on for some durations ahead. So this will cause the beans to be over processed. So it will produce instead the beans that is not favorable in terms of aroma and also taste. So that is what means by termination of residual chemical reactions. And number two is retention of volatile aroma compounds. So, and then prevention of the baked flavor profile. So when a coffee bean is called baked, it means that it has lost the taste. So basically, you're just eating, no, drinking a how to say it, charcoal. So you're just drinking charcoal. Furthermore, so that is why the cooling is very important. And also number four is thermodynamic milestones and methods. So basically, there are two roles in the cooling of roasted beans. So there are the 4-minute rule. So basically, the beans should reach 40 degree of temperature in 4 minutes. But this is very hard to attain using simple means. So there are ways to cool it using water quenching, but actually using water cooling, there are risks of reducing the taste and also the aroma that has been uh, produced by the beans. So the cooling itself has to be done in a controlled manner. Why? The first reason is uniformity. So the cooling should be done gradually to prevent uneven flavor development within a single batch. And also, batch-to-batch consistency is very important as well to be attained. This is why we control the cooling. And also the quenching. The quenching is offering high precision for reaching a specific temperature. It has a problem of washing away delicate oils and flavor compounds. It means even though quenching will cool down the roasted beans a lot faster than air, but it has the risk of washing away the taste of the coffee as well. And also, controlled cooling also provide the time for the beans of the resting period. Resting period is where the beans will be stabilized and develop more flavor profile. So basically, why should a cooling be controlled? It is because we need to keep the beans at some temperature quickly, so it will lock in the taste. So, of course, there are methods of cooling. If you're using manual ways to do cooling, it is much exhaustive. I mean, you can always use the hand-operated fan for cooling, but since the cooling should be done fast, it is not. It is very tiresome to do, especially if it's a SMA, a small medium enterprise, which with very limited resources. So the advantage of do mechanical cooling is the first one is rapid temperature reduction, and also the flavor and aroma preservation, environmental control, improve workplace safety, and also consistency for industrial batches. Since we use mechanical cooling, the consistency will be kept because machine will operate just the same every time as long as it's been maintained, not broken down. Also, there are disadvantages of the mechanical cooling as well. So the first one is the technical complexity. I mean, it is not very easy to design a mechanical cooling mechanisms. And also there are the problem with the design and efficiency risk, and also maintenance requirement. Because it's a machine, it requires maintenance time to time. Because with less maintenance, the machine will keep breaking down. And there are also the risk of flavor washing. I mean, even if we are using water, we are using air to cool down the roasted beans. If the flow of air is very fast or very rapid, there is a chance as well that the flavor being washed away by the air. Okay, so that is about the cooling. So up to this point, we have discussed about the coffee production, the coffee processing stages, which is in the roasting phase. And also we talk about the cooling, which is part of the coffee process. So if you are doing a coffee roasting, you should do the cooling as well, because you don't want the taste to be changed after roasting. Okay, next we will talk about the control system, since we are talking about the IoT, right? So we will start with the control system. A control system is an interconnected components that manage, command, direct, and regulate the behavior of a device or system to provide a desired system response. Well, simply said, a control system is a system to be used to control a variable. The variable itself could be anything. Could be a temperature or a liquid level, could be a pressure. There is a lot of variable that can be controlled by control system. So basically, a control system is a system to control that. That includes movement system. So movement, the mobile system is also is a control system. I mean, it controls the position of a system, right? And also, there are two kinds of the control system. There are open loop control and closed loop control. The open loop control is where the control action is independent of the output of the system. I mean, the input is not determined by the output of the system. Well, for example, is the common stove. So when you turning on a stove, it will keep turn on as long as you don't turn it off, right? So this is the example of the open loop control. So if there's a control system that does not turn off after a set point is reached, that is an open loop. There's a lot of them. For example, the lighting in your room. So if you switch them on and it doesn't turn off by itself, it is called open loop control. So most of the traditional control systems are open loop control. And the newer one is called closed loop. Closed loop control is based on the feedback mechanism. So we can read here that the control action of a closed loop control is dependent on the output. So basically, the input or the control of the system is dependent on the output. Usually, there's a set point or a set value to be reached, and it will modify the behavior of the system. So one of the example of this kind of closed loop control is a AC, aircon, uh, air conditioner in your room. So when you're using an aircon, usually you will set a say a degree, a temperature that you desire to be attained. So when you have set it, so basically the environment is not on that temperature yet, right? The first time it's turned on. So it will continue to work until the temperature is reached. So after the temperature is reached, there are the modification of behavior of the system. After there is a reach set point. So that is what the closed loop control. So as long as there are feedback mechanism, it can be called closed loop control. So what does it tie to automation? So the control system is the only thing that enables automation. So this is what is doing the automation itself. So it will manage, it will command, it will regulate the behavior of the devices without human intervention, or at least without constant human intervention. So like in your AC, so once you set it to say some temperature, it will continue to work with or without your supervision, right? So this is what enables the automation to be done. And automation itself is needed to reduce the human decision making in some process. So usually, control system will provide the logic and the loops. Loops here means the process, right? The process that is required to make the system function as reliable and as accurately as possible. There are four critical key functions of control systems in automation. The first one is enabling continuous and automatic operation. So this is where the function of a control system is being used. It is being used in industrial processes or in cruise control. And also, number two is in logic and sequencing for task execution. Most of the time, the control system will take over the human intervention to the system. So basically, it will take the thinking process, well, not all of them, partly, so that we don't have to intervene with the process. So such process is attained by using of sequential control, which means control of sequence. So, and also the using of PLCs or programmable logic controllers. And also, in terms of automation, the control system will provide a function of large-scale coordination. using a system like a distributed control system and supervisory control and data acquisition system. These two different system is actually so much different, but actually in most of the industry, both of these systems are used in tandem. I mean, what means by in tandem is they are used to in the same time. I mean, DCS will be used to take control of the operations, while the SCADA or SCADA it will take the process of the data acquisition and analysis. So basically, you can say that the DCS is the nerve system of the industrial system, and the SCADA is the brain of the industrial system. And the last one, the function of control system is the digital and modern advancement. So this is the critical key functions of control system in automation. There is in automation and also in the use of a control system, we will know the terms like sensors, actuators, and microcontrollers. So most of you must have known this term as well. But to be explain it simply, so the sensors is your senses. It will measure the variables. It will measure the temperature, measure the proximity, measuring the movement of an object. So the sensors will act as the sensors, and the actuators will act as the muscles. The actuators are the ones who make the change happen. So the actuators usually the final control elements that actually control the process. I mean, if we are talking about temperature, so the actuator should be the heating system, and also if we're talking about the movement, the actuator should be the motors of the machine, and so on. So basically, what make the changes to happen are called the actuators, and the microcontrollers are called the brain. So this is the part of the control system that is taking a decision-making part in the system. So it take over the brain function of a user. I mean, the human intervention. So this is usually a complete computer on an IC that will act as a control unit. So usually inside the microcontroller, there will be an algorithm that decide how the system would react. And these three part usually exist in the control system. This is also what enables the control system to do automation and reducing the human intervention. So in a closed loop, it is usually going through this process. It starts from sensing. So after sensing, it will go to the processing. So the variables that have been sensed will be sent to the processing system, and then it will make a decision, and the decision will be carried out by the actuators in actuating. So and then in the term of feedback, so what has been actuated or what has been changed by the actuator will be then measured. Has it reached the set point? So that is what called by feedback. So it'll be back to sensing. So basically, the output of actuating will be compared by the set point, and also the parameters that have been sensed by the sensor. That is called feedback. So the process that I've been done here will be fully dependent on the feedback. So for the last part, for the control system, there are actually a lot of parameters to be used in measuring how the control system perform. But in my research, I use these three variables, these three measurements: the response time, time constant, and rise time. So these three parameters will actually be used to see how reactive and how fast the system are, and how is the quality and the consistency of the system and the predictability of the system. So we can read the definition here, but if I read it all to you, so it'll take a lot of time. So basically, these three variables will determine or will show these parameters of the system. Okay. Before we move on to the last part of the presentation, is there any question?
Hi, sir. The question will probably be asked after the presentation.
Okay, okay. So this is my habit in the class. Usually, I will ask people to give question in middle of the presentation. Okay. So as an example, I have these two research that have been published just not so long ago, last year, in this conference. So you can access the paper here. I believe the co-study people will provide you with the file. So the first paper is about the automated temperature control. For the roasting machine, we are using the green coffee to be roasted, and also the LPG or LNG, liquid natural gas for burner fuel, and batteries for power source and fire ignition, and also adhesives, bolts, and screws as fastener. These are the control parts that we are using. We are using RTC for the clock or timekeeping of the system, and we are using MAX 6675 temperature sensor, and also we are using ESP32 microcontroller. This is very popular if you are using automation of control. And we are using a gas burner and servo control valve. The SCV will be used for gas burner control. And 16:2 LCD panel. This is to display the data, the temperature, and also the set point. We are using also the dimmer speed control. This is used to control the servo, and this motor servo as well, and power supply, and we are using also the step down regulator. What was done in the research? We are planning first, and also the design. We are planning, and then we are getting materials to be assembled. So we are buying the sensors, the other parts of the system, and so after we gather the material, we assemble the components of the control system, and after we assemble the components, then we will write the code into ASP32, And after that, we are implementing the system, which means actually installing the assembled components of control system into the roaster machine. And then we are testing it using the install system. So we are using only 1 kilogram of coffee beans, 50 minutes each, which I have set point of temperature 110 degrees Celsius. And this is repeated 3 times. And in data analysis, we record the temperature, and then from the temperature, we'll determine the response time, time constant, rise time, and the ability to maintain temperature. So this is the roasting machine that has been designed. This is the control. This is the control system placed in here, so it's be isolated from the whole. So the roasting machine actually have the 4 kilograms of maximum capacity. Initially, the roasting time was 15 minutes, 30 minutes, and 45 minutes. And thermocouple is installed within the drums to monitor the temperature. And stove burner is set down here to roast, to do the roasting. This is the control of the design. This is the design of the control. So when the machine is start, the temperature, the set temperature and the roasting time will be set, and then the burner is turned on. Time to time will be checked if the temperature has reached 60 degrees. So if it has not reached 60 degrees, it will be still turned on. But if it has reached more than 60 degrees, the blower will be turned on to 50%. So actually, the blower is turned on. So the beans are not burned. And the same as this process, the process will be checked time to time if the temperature is 100 degrees Celsius already. If it hasn't, it will the blower will continue to operate on 50%. If the temperature already reached 100 degrees Celsius, the blower will be turned to 100% of its capacity up until 110 degrees Celsius. So when the set point of 110 degrees Celsius is reached, the burner will be set to the minimum. And then if the time is already 50 minutes, will be ended. But if it's not 50 minutes, the burner will still operate until the 50 minutes time is reached. And that's the end of the control. So usually this should be done manually. The operator will check the temperature time to time to make sure that the temperature is reached as intended. But using this control design, we don't have to. This is the schematics. So this is the microcontroller. Then this is how it is been linked and connected to the LCD. And this is the temperature. And this is timer. This is the buzzer. This is also the buzzer. And this is the switches. And this is how the assembled control system look like. So if we zoom it in, you can see here, this is the ESP circuit that's being used. And this is the initial display. So firstly, when the machine is turned on, It will have the temperature. It will display the temperature and also the time. This is the goal, the set point, because it is initial, so it didn't have the set points first. So after set, it will show the 110 degrees Celsius of set point and also the time of 50 minutes. This is the temperature profile of the machine. So this is the dump temperature and the blow temperature, because we couldn't really measure the temperature of the beans. So it will rise first from 40 degrees, and this is the set point of 100 degrees, and this is where the charge phase begins up to the turning point, and we continue to rise to the first crack and the roasting end here. So actually, the temperatures are a bit lower than it should be, but we haven't really evaluated the beans that it produced here. But my students say that it's being doing the research here. It is consumable, which is very very reassuring. And also in terms of making sure that the temperature has been controlled well, we are using the single sample t-test here. So from the t-test, we can see that actually the temperature has not been, the system has not been able to maintain the temperature at 110 degrees. So since the system is actually designed to maintain the temperature at 110 degrees, here, even though we can see it 120, it reached 120 at the end. The system couldn't really maintain the temperature here. So I guess in the future, it will be furthermore developed to maintain to the intended temperature. And this is the response time, 16 minutes in average to reach a set point of 110 degrees. The time constant of 69.52 degrees in average 10 minutes. And the rise time is averagely 11 minutes to reach 99 degrees from 44 degrees. Even with the system's inability to to maintain the temperature, the coffee produced itself is acceptable. And this is the second research about the cooling machine. So in the terms of the cooling machine, it is much more simpler. We are just using coffee beans to cool the machine or cooling machine. And also we are using a coffee beans cooling machine, and the system is installed into the cooling machine. So we're using the different temperature sensor here, ES80P20 temperature sensor, and ESP32 microcontroller. We are using the same microcontroller. We are using the same panel and relay modules as well. And the steps of the research is almost the same. We are ongoing planning into the testing phase. This is the cooling machine. This is a error of the this is the error. So this should be the cooling machine. So this is the cooling machine. So basically, it's just a pan with the stirrer. This is the stirrer, This is there, and this is the blowers. So the cooling of the beans is expected to happen with the beans being stirred, and also blowers expected to pull off the beans. So the machine is expected to have the 3 kilograms of maximum capacity. So when the thermocouple was installed, thermocouple is installed in the bottom of the tray to measure the temperature. The stirrer itself is being used to make the temperature be evenly dissipated. So this is the control panel. It is a lot smaller than the previous one. This is the control design. So when the system has been started, temperature has been set, and the blower is set to 100% the first time. So we check if the temperature already reaching 45 degrees or not. So if the temperature is still higher, the blower is still be on 100%. After the temperature of 45 degrees is reached, the blower will be reduced to 50% capacity by reducing the voltage to 3 volts. And then it will continue to operate and check if the temperature already 35 degrees or not. So as long as the temperature has not reached 35 degrees, it will be still operating at 50% capacity until it reaches 35 degrees or lower. And after that, the system will be turned off, and that is the end of the process. So it is a bit simpler than the roasting machine. This is how the system block has been designed. This is the schematics. You can see it here. This is the ESP32 connected to the LCD, and also this is the relays for the blowers, and this is the buttons. This motor DC for the blowers, for the stirrer, and as this is the voltage regulator. This is for blower 1 and 2. So basically, it will continue. This part will maintain the control on the blowers. This is how it's assembled. These are the relays, and this is the ESP32 circuit. This is the program temperature. So initially it will say 0 degrees, and when it's been set, it will be set. This is the first time operating up to the set point degrees. But basically, this the system is hardwired to detect until 40 or 35 degrees. This is the temperature profile. So the first time the roasted coffee beans are above 90 degrees, this is the average temperature, so it's around just 90. So it will gradually sharply decrease to under 60 degrees in 10 minutes. So, and it continued to cool down. This is the control one, cool down. So when this temperature is reached, this temperature is reached, the blowers are set to 50%. So basically, we can see that it's not as steep from this point onward. It's not as steep as before. So, and after the 40 degrees has been reached, the machine is stopped to operate. And the response time is 35 degrees Celsius was reached after averagely 40 minutes from the 90 degrees Celsius starting temperature. while the initial temperature was actually around 200 and 100 degrees, 200 degrees. And the control of temperature here has been successfully done by reducing the voltage of the blower from 3 volts to 5 volts, where and it is reached within 20 minutes here, and the final temperature is reached by another 20 minutes. So this is a lot slower than intended. The ideal time to be needed in this is 4 minutes. So actually the temperature of 40 degrees should be reached in 4 minutes, but this one is taking a lot longer to reach 40 degrees. It needs like 25 minutes. So in the future, this cooling machine will be added more blowers to do much more rapid cooling, and also we will use as well perforated basin instead of the solid ones to let the airflow to be able to cool down the coffee beans a lot faster as well. So that is my presentation. So if there is any more inquiries outside of this class, if you want things to ask of me, you can contact me from my email here, lukmanadlin@usu.ac.id. I will try to reply promptly. And I think that's all. I give back the control to Miss Johanna.
Okay, thank you very much, sir, for the presentation. Okay. Let me share my screen. Okay, everyone. We have heard and we have also seen the explanation from Dr. Lufman regarding his materials. I'm sure it's very innovative and also very insightful. And I would like to welcome everyone to share their curiosity or feedbacks in this Q&A session. I will be reading through all of your questions, and afterwards, Dr. Lukman can answer to it straight after I read it. Okay, I have seen some questions. The first one is actually from Rifda. She asked two. She said, Dear Dr. Lukman, what an insightful presentation. I would like to ask for two things. The first one, you compared fast roast or high acidity and slow roast, which is increased body. Which profile was the automated system's logic designed to target, and how does the current temperature fluctuation affect the consistency of these flavor notes? And the second question she asked, the presentation says that if coffee stays hot for too long after roasting, it can lose its sweetness and taste baked or bitter. Since your current cooling machine takes 40 minutes to get the beans to a safe temperature, how do you keep the coffee from losing its special flavors while it waits to cool down? Okay, for Dr. Lukman, you may answer the question.
Okay, that is actually the question to be answered in the next research, but thank you for clarifying. So the which roasting method is being used in the roasting machine? We are using the fast roast because we are actually using a very high temperature first to roast. So before the 110 degrees, the beans are not inside the roasting machine. So we are using the fast roast. And for the question number two, and how does the current temperature fluctuation affect? Sadly, we didn't really test for the flavor. at this point, we are testing only for the use of this system to control the temperature only. But I guess in the future, we'll be testing for the flavor as well. But thank you for clarifying. And also, the person says that if the coffee stays hot, okay. Yeah, well, the temperature is a lot, the temperature is reached a lot slower. I mean, it should be on under 40 minutes. But since we didn't really officially tested for the flavor, uh, aside of the personal use, my student said the flavor is not much different than those that has been roasted by the professional roasters. I mean, uh, it is largely because we don't really have the capability of the determining the change of the flavor itself, and this requires a lot more steps of research to be done. So at this point, we are focusing on the use of the automated system to do roasting and cooling only. As for the quality, I think we'll reach that point in the future. Thank you for the question.
Okay, thank you very much, Dr. Lukman, for answering the question. And also thank you, Rifda, for the questions. I hope that answers your curiosity. And then the next one, there are also two questions from Shafira. She asked, Dear Dr. Lukman, thank you very much about the interesting yet insightful presentation. It's nice to learn more about the coffee production, especially in the regional area of Indonesia. I have two questions. The first one is, you mentioned that Indonesia's coffee productivity is 4 times lower than competitors like Vietnam. How do you believe the implementation of these automated roasting and cooling systems specifically addresses the underlying causes of this productivity gap, such as aging trees or smallholder dominance? And for the second question, given that 99% of the industry is dominated by smallholders, often lacking modern technology, what is the estimated cost to benefit ratio for an SME to adopt the ESP32 based automated systems that you designed? That is all, sir.
Okay, this is interesting. The first one, if you're addressing the productivity gap, this is a bit far-fetched. I mean, this use of IoT is on the end point of the production. So, but you're asking for the starting point. So, I guess I couldn't really answer this because uh, my design system doesn't really address this problem. But I guess it really depends wholly on the innovation of the government. So interesting question, but I couldn't really answer your first question. Number two, so given the 99%, this is also interesting since we didn't really calculate the cost to benefit ratio. But since the cost of the machine is very low, I'm not sure about the roasting machine. Roasting machine costs only like 7 to 8 millions, and also the cooling machine costs a lot lower. I guess it's 3 to 4 millions rupiah. So basically, it should be very cheap enough to be bought by the small industries. And also, given the high yield of the machine, um, it should be able to help not the farmers, but the coffee processors or coffee roasters to uh, do the roasting and cooling process themselves without a lot of people not a lot of labor to be involved in the process. So in the end, it will help to reduce the cost. And I couldn't really give you the numbers, but if we want, we will try to provide the calculation a lot later. Thank you.
Okay, thank you very much, sir, for for the answer. I mean, and then also thank you, Shafira, for the question. I hope the answer satisfy your curiosity. And as Dr. Lukman said, if you need more explanation, you can just email him to the email that he has provided. And then the next one, there is a question from Sasha Asia. I'd like to ask a question. So you mentioned that the cooling machine took 40 minutes to cool 2 kilograms of bean 4 minute roll. And curious, how does this 40-minute duration affect the bake flavor profile or the retention of volatile aroma compounds?
Okay, thank you. So thank you for the question, Shada. So basically, I have the same question as well, because we didn't really test for the flavor itself, but this is uh, the part where we are trying to improve in the future. So basically, I'm really sure that there should be some effect to the flavor of the uh, coffee, but because we didn't really measure the changes, uh, we couldn't really say how is it affecting it. But in the terms of the appearance, it is a lot similar than the ones that has been called by the roasters. But since we didn't really test it out, I couldn't really answer your question.
Okay, thank you very much,
Okay.
sir, for the answer. I hope Sasha can get the answer that she's hoping for, but I guess there's needed to be more research regarding that. And then there is also a question from Melodia. She asked, Dear Dr. Lukman, thank you very much for your insightful presentation. I would like to ask a question. The presentation mentions that water quenching over high precision, but risk washing away delicate oils. Why did you opt for a mechanical blower and stirrer system instead of a controlled quenching system for this SME case study? That's the question, sir. You may
Okay,
answer.
thank you. Thank you very much. Melodia, uh, water quenching involves the use of water instead of the air. So basically, this is why we opt for mechanical blower instead of the use of water. So usually, if you want to cool down the coffee a lot faster, you can use a flow of water to cool down the beans a lot faster. But since we are not risking the wash away oils that creates flavor of the um, coffee in the process, we are using the air cooler instead. So cooling using air. That is why we are using the blower and stirrer system instead of the water system. Thank you.
Okay, thank you very much, sir. I hope that answers your question, Melodia, in the chat box. So I will ask my own personal question, sir. Uh, I will read it. So you mentioned that fast roasts are better for high altitude beans to keep their fruity notes. So can your current automated system be programmed to switch between a fast and slow roast depending on what kind of beans the farmer has? That's my question.
Okay, that is a fantastic question, actually, Johanna. Since we provide the set temperature and set time for roasting, it can be set easily if there's a need to adjust to the type of the beans that has been processed.
Uh,
So I guess I can say it's possible from the system that has been provided.
Okay, thank you very much, sir. And there's also one more question that I would like to ask. So your
Mhm.
data shows that 70% of coffee areas in Indonesia need renovation because the trees are too old. So do you think technology like yours can help farmers make enough money to finally afford to replant their farms with newer and better trees?
Uh, okay, this is a very hard question to answer, but there are two key points of the machine that we've been developed. One, it is much cheaper than available machines of the roasting machine. So average roasting machine would cost like 20, 20 to 30 millions. So when ours is only like 7 to 8, so maximum of 10 perhaps if we include other systems inside. Uh, if you are asking, could this help? I think in the current price, it should be, but we are talking about the long term, right? Uh, I'm not really sure in the long term it will be very helpful since the roots of the problem itself is not with the coffee processing, but the coffee production instead. So it's within the plant. So even though coffee, if they don't produce it,
Okay, thank you very much, sir. That really answers all of my question. And also, I see here that there are two more questions from Melodia and Sasha. Melodia asked that thank you for the answer, Dr. Lukman. I have also another question. You use the the Max 6675 for roasting and the DS18B20 for cooling. Why were these specific sensors chosen for their respective environments, and did their response times significantly impact the system's overall rise time? That's the question from Melodia, sir.
okay, thank you very much. So, uh, your your question is about if response time the answer is no, since Max 675 and DS18B20 is used for different reason. So the use of Max 6675 is used for because we need to measure a lot higher temperature. So Max 6675 operates on 0 to 124 degrees Celsius, while DS18B20 operates lower, which is from minus 55 to plus 125 degrees Celsius. So it only reflects the range of the temperature instead of the response time. So for the response time itself, it is that it doesn't really affect it, but only the range of uh, the range of temperature. I guess that's the answer. Thank you.
Okay, thank you very much, sir, for the thorough answer. I hope that satisfy your curiosity, Melodia. And then the last one, there is a question from Sasha. She said, I have a follow-up question, sir. Based on the evaluation results of the roasting machine, what improvements or optimizations do you plan to implement in future developments to achieve more stable temperature control?
Okay, thank you. Thank you very much, Shasha. So I think my presentation doesn't really cover what's inside the paper. So in the paper, we mentioned that we need an extra outlet, so control outlet to let uh, the temperature to dissipate a lot faster. So since we are using drums, so the air that has been trapped inside the roasting machine couldn't be exhausted fast enough using the current system. So if you're asking what to be implemented in the future to achieve stable temperature control, uh, I think we will develop a way to control the airflow more efficiently than the current system, since the temperature dissipation is not very well because of that problem only. So I guess that's my answer. Thank you very much.
Okay, thank you very much, sir. I hope that answers your question, Sasha. So yeah, as I see here in the chat box, there are no more questions from the participants. So we will close the Q&A session. Thank you very much, everyone, for the questions, and thank you very much, Dr. Lukman, for the answers. Okay. Moving on, we will be taking a group photo before we end our meeting today. So I hope everyone can turn on your cameras so we can take a group photo and also use the virtual background that have been provided by my colleagues in the chat box, I mean. Okay, let me stop my screen first. Okay, I encourage everyone to turn on your cameras and also use the virtual background. But if you are unable to use it, it's okay. You can just turn on your cameras. Okay. While we wait, I encourage everyone to follow our Instagram, which is pasita.education. You can get more information regarding our meetings like this and and also there are other projects that we do. So yeah, you guys can take a look at our Instagram at pasita.education. Yes, everyone, please turn on your camera. It's okay if you cannot use the virtual background. Okay, one more time, guys, please turn on your camera. It's fine. You don't have to use the virtual background, but I encourage you guys to. And don't forget to follow our Instagram at pasita.education. You can get more information regarding meetings like this in the future. Okay, I think that is all that can open your cameras. My colleague Shafira will help us to take a picture of this session. So yeah, Shafira, I will count from 1 to 3. She will do it. Okay. Everyone smile. 1, 2, 3. Okay, and one more time. 1, 2, 3. Okay. Lastly, 1, 2, 3. Okay, thank you very much, everyone, for your cooperation today. Let me share my screen one more time, one last time. Okay, thank you everyone for attending and participating in the International Perspective webinar series titled IoT Use in Coffee Production, a Case of SME in North Sumatra. I also would like to thank Dr. Lukman for coming here and giving us the materials and such insightful presentation. Don't forget to fill in the attendance link to get your certification of participation for the participants. The link will be provided by my colleagues in the chat box. Thank you very much, everyone. Good afternoon.
Good afternoon. Thank you very much. See you, everybody.
See you, sir.
Thank you, sir.
You're welcome.
Tulog na.
everyone.
Mel, mag-leave ka na, Mel.